a change of state occurs due to the application or the removal of heat. Okay. So these are some of the questions that we'll have to deal with when we talk about thermal properties of matter and what happens when a certain amount of heat is applied or added or removed from the system. So since we have smoothly and gradually have come to the conclusion that heat is actually a form of energy which flows or which gets transferred from one body to another or from a body to its surrounding, and because of which the temperature changes of the concerned body. So how do we measure this temperature? So let's talk about measurement of temperature, which is our second topic of discussion as I have written it down earlier. So to measure temperature, we would need a device which is called as thermometer. All of you know thermometer. When there is a rise in temperature of the body, you must have always used it in order to measure the temperature of the body above the normal one in order to assess that how much of fever one has. And so thermometer is not a new thing. It's only that we have to understand that how it works. What is the principle on which it works. So as again as said that it's so we'll use it using a thermometer. So again this part means heat, which is slight variant of that, which is thermos, and a meter means a measuring device. So the most common form of thermometer is mercury in glass thermometer. So let's just see that. So mercury in glass, it's written like this. So mercury in glass thermometer, so which uses the fact that this mercury, which is liquid, would the temperature when the temperature increases, the volume of mercury will increase, or the mercury will expand as the temperature is enhanced. So this change in volume or the expansion of mercury is used to indicate the temperature of a body. And so it consists of, we'll draw it very soon, it consists of a mercury filled glass bulb which is connected to a capillary tube. Okay. So when the mercury is heated, then it expands into the capillary tube, and with this amount of expansion being proportional to the change in temperature or the rise in temperature, and the outside of the glass in which the mercury is there. So outside of the glass is marked with divisions, so that we know how much of expansion has occurred compared to its initial situation before the application of heat. So basically these are that's pretty much the working principle of a mercury thermometer, mercury in glass thermometer. So the popular choices for measuring these temperature are two, namely the Celsius scale and a Fahrenheit scale. And the way we can understand them is the following. So, let us draw a thermometer here. So, this is the mercury, and so this is so this is a mercury filled bulb which is enclosed in a glass tube, and the glass tube has marking here. I'll do the marking in a while, and so this shaded part is the mercury. So, when you dip this end onto a hot object, this mercury will expand, and how much it expands will be shown in a scale that is on the outer glass of this thermometer. So, this is one. I will draw another in order to explain the two scales of temperature. So, let us call this as Celsius scale, and let us call this as Fahrenheit scale. By the way, this Celsius was formerly known as centigrade. So, this used to be called as centigrade scale as well. So, I have drawn two such thermometers, and now I have to do the markings or the readings on the outer glass, the capsule of the thermometer. In order to do that, now these two thermometers, keep in mind that they measure from the ice point to a steam point. I will define what they are. So, so when ice melts at 1 atmosphere of pressure, that is called as the ice point. In the Celsius scale, that is marked as 0 degree C. C would correspond to Celsius. Okay? And so, this is one of the points in that scale, and the other point which is called as the steam point, where water starts to boil, and this is again at 1 atmosphere of pressure, and this is called as 100 degree centigrade. So, there are 100 divisions which are marked on the on the outer wall of the I of course not going to mark 100 divisions, but there are 100 divisions in between these two, namely the ice point, which is here, and the steam point, which is here. Okay. And the same thing in the Fahrenheit scale is at, so I will draw it to scale in this, it is at 32 degree Fahrenheit and 212 degree Fahrenheit. So, this is steam point, I will just write steam for now, and this is ice point. I simply write it as ice. So, these are the two scales that are commonly used. It can be, you are all familiar with this, when you see news in either in television or you actually read news in newspaper, in India, the outside temperature or the temperature of the day is always quoted in Celsius, while in United States of America, it's mostly quoted in Fahrenheit. While it's also true that the body temperature is never quoted, usually never quoted in Celsius, and the body temperature is quoted in Fahrenheit. And the normal body temperature of any healthy human being is 98.6 Fahrenheit, degree Fahrenheit, which corresponds to 37 degrees centigrade. So I'll tell you this relation, and from there we'll also try to derive a relation between the two scales. Okay, so human normal human body temperature is 98.6 Fahrenheit equal to 37 degrees centigrade. But mostly, as I told you, that medically this is quoted all over the world. Now, just to have a comparison between the two thermometers, I hope to have drawn them to scale. That is, the length of the thermometer is same in both the cases. The mercury is shown here. So the ice point, or which means that the water starts freezing or the ice starts melting at 0 degrees centigrade here, and the water starts to boil or steam starts forming at 100 degrees centigrade. And the same is at the Fahrenheit scale, it's at 212 degree Fahrenheit for the steam point and 32 degree Fahrenheit for the ice point. So now it's worth mentioning that a degree centigrade, one division in the Celsius scale, I am using centigrade, it's actually Celsius, 1 degree in the Celsius scale is a greater than 1 degree in the Fahrenheit scale, because there are 100 degrees and as opposed to so 100 degrees or 100 divisions in the Celsius scale which corresponds to 180 divisions, which means 212 minus 32, 180 divisions in the Fahrenheit scale. Thus, a Celsius scale is 180 divided by 100, which is 9/5 times larger. So, one division in the Celsius scale is 9/5 times larger than that of a Fahrenheit scale, and this could be easily used in order to draw a relationship between the two scales. And in order to do that, let's write down a formula which is fairly simple and must have seen it somewhere. That so C, let's talk about the temperature in Celsius scale to be C, which is equal to F minus 32 multiplied by 5/9. F minus 32 was done to offset this the two ice points to be same, because the ice point is 32 Fahrenheit, whereas this is 0 degree centigrade. So, in order to offset that, we have subtracted 32 from the Fahrenheit reading, and it has to be multiplied by an inverse of 9/5 in order to get the reading in the Celsius scale. So, typically we have a C/5 equal to F minus 32/9 is the relationship that is there between a Celsius reading for temperature to a Fahrenheit reading for temperature. So you can understand that a reading of minus 20 degree centigrade, so a minus 20 degree centigrade would correspond to which is so a minus 20 over 5 into 9 is equal to F minus 32. So that would be giving me 9, so this is minus 180 over 5, which is minus 36 equal to F minus 32. So F is equal to minus 4 degree Fahrenheit. So a minus 20 degrees centigrade is equal to a minus 4 degree Fahrenheit. That's the conversion. All right. So this is the relationship between the two scales, namely the Celsius and the Fahrenheit scales, and one can use this relation in order to get any temperature reading in one scale and convert it to another. So let's talk about a third scale of temperature, which is not used in day-to-day life, but it has enormous scientific importance, and you would understand about the scientific importance in just a while. So this is called as Kelvin scale. So the Kelvin temperature scale. All right. So the Kelvin temperature scale was proposed, or rather introduced by Lord Kelvin, who's a Scottish physicist. And each division in that scale is represented by a Kelvin. So each degree or each division, whatever you want to call, is represents 1 Kelvin. And please do remember that it is not degree Kelvin, it's simply Kelvin. And the reason is that in SI unit, using the 3 base units such as that of length, mass and time, temperature cannot be expressed. So in the SI unit, this is taken as a 4th base unit, which is temperature. This T is not temperature, it's time. So you have to have another one, temperature, in order to have a base unit for temperature in the SI unit. So that's why it's not degree Kelvin, it's simply Kelvin. So when we quote a number, say 200 Kelvin, we just simply say 200 K by the letter capital K, where K is after its inventor Kelvin. All right. So why is it important, and why is it introduced in scientific content, and why can't we simply do with the Celsius and the Fahrenheit scales that we have introduced earlier? There is, as I told, that there is a certain amount of importance associated with this, and so 1 Kelvin is same as 1 degree centigrade. So the divisions in the Kelvin scale is same as that of the Celsius scale. Every now and then I keep making this mistake of saying it's centigrade, but please do understand it as Celsius. But they are same. It's just formerly known as centigrade. So how the concept of absolute temperature is used using the Kelvin temperature scale. So one can define an absolute zero temperature below which no physical substance can exist. So, it is not physically possible to go below an absolute zero, which is the zero of the lowest temperature in the Kelvin scale. Remember, when we talked about the Celsius scale and the Fahrenheit scale, we really talked about a 0 degree centigrade to 100 degree centigrade and a 32 degree Fahrenheit to 212 degree Fahrenheit, and both were benchmarked against the ice point at one end and the steam point at the other, while there are lower than the ice point that is possible, and like the temperature can go up to minus 30 degrees Celsius in cold countries such as Canada, and there could be a temperature which is much more than 100 degrees centigrade. The fire on the oven has temperature much more than that, while a mercury in glass thermometer is unable to measure that. So, scientifically, even if we don't need them in day-to-day life, scientifically it's important to talk about temperatures which are lower than 0 degree centigrade and larger than 100 degree centigrade. And this is exactly that the Kelvin temperature scale does exactly that. So, there is a conversion that is possible between the Celsius scale and the Kelvin temperature scale, and the relationship is very simple. It's a linear relationship. It's 273.15. Okay. So, this T is the temperature in the Kelvin scale, Kelvin temperature scale, and Tc is the temperature in the Celsius scale. So, any temperature in the Celsius scale has to be added this number 273.15, which is an experimentally observed number, in order to get the temperature in the Kelvin scale. Okay. So, an ice point where Tc is equal to 0 corresponds to 273.15 Kelvin. So, this is in Kelvin. So, this is 273.15 Kelvin is the ice point in the Kelvin scale of temperature, while the steam point is 373.15 Kelvin. And since we know the relationship between the Fahrenheit and the Celsius scales, we can also convert it, convert a absolute scale or the Kelvin scale of temperature to its Fahrenheit counterpart. Usually that is not required. So, just to have these pictorially representing, I am showing you a cartoon of these two temperature scales. So, this is 273.15 Kelvin, which corresponds to 0 degree centigrade, and this is a 373.15 Kelvin, which is equal to 100 degree centigrade. So, these are the conversions of these two temperature scales that are of relevance for us. Now, as I told that this 273.15 is a number that is almost pulled out from the hat, or just pulled from nowhere. We are now going to justify this number and how it comes, and as I told that it's an experimental fact, and the experiment can be demonstrated by doing a constant volume gas thermometer, where these number would be justified. So, let us discuss constant volume gas thermometer. So, So when a gas is heated, or it's some temperature or some heat is applied to it, the pressure of the gas increases. And when the gas is the heat is extracted from the gas, the temperature is lowered. Okay, and assuming that the gas is kept at a constant volume. Okay, so it is kept inside a container, and the container has a fixed volume. So this is the basis for so the change in the gas pressure with temperature is the basis for measuring this or using this constant volume gas thermometer. So let's see that how it looks like. So this is a vessel, a container. The container has some substance, let's say it's a liquid for now, whose temperature needs to be measured, and you can you need to know the so this is at a given temperature and we don't know the temperature of this, and there is now another container inside it which contains a gas this contains a gas and the gas is this is connected to a U-tube manometer which looks like this. So there is mercury here, and there is sort of mercury all the way here. So this is mercury. Remember that while we talked about measurement of pressure, we have introduce these U-tube manometers, which are usual devices that are used for measuring pressures, and this is the same manometer, U-tube manometer. There is a reference level which is here of mercury, and this height is h, and this is an evacuated space. This is the glass filled bulb, oh sorry, the gas filled bulb. So this is a gas filled bulb here. This is immersed in a substance whose temperature is to be measured, and because this gas is immersed in this substance or the liquid, as the temperature of the liquid rises, the gas will expand, and in order to keep its volume same, we'll have to adjust the right hand of the manometer tube, the level of mercury in the right hand of the manometer tube, so as to keep the reference level same, and this height h will be the indicator of the pressure that the gas is exerting on the liquid. So the change in temperature of the substance will be proportional to the pressure. The change in temperature will be proportional to the pressure, and since the pressure is proportional to the height difference between the reference level and this level on the other hand of the right hand of the manometer, so this temperature difference in the substance will be reflected in the height of the mercury in the right hand of the manometer with respect to the reference level. So this is a simple working condition of a constant volume gas thermometer. So what is seen is that if one does an experiment with this setup, so it is seen that the pressure which is proportional to the, as I told that the pressure is proportional to the height, and the height one can measure using a scale. So this pressure is, so this is the pressure which, as I said, is proportional to the height, and this is the temperature, and let's say we denote it in degree centigrade. For now, it will show, so this is the 0 degree centigrade, this will show linear behavior in this, so this is say 100 degree centigrade, and this is 200 degree centigrade, and so on. Okay? So it will show linear behavior. The pressure will increase linearly as the temperature of the substance is raised or it's enhanced. So it will meet the y-axis at some point. Okay? Now, if we imagine a negative temperature scale, which does not happen, but suppose we talk about a negative temperature scale and extrapolate this line to the x-axis, to the temperature axis on the negative side, this will meet the x-axis at 273.5. So this value is 273.15, sorry, 273.15. And why is it called as absolute zero? This 273.15 in the so this minus 273.15 in degree centigrade. So you remember the relation that we have written down earlier. So T equal to Tc plus 273.15. So now here Tc is equal to minus 273.15. If I add it to 273.15, it becomes equal to 0 Kelvin. So this is in Kelvin, and we get a 0 Kelvin. And this 0 Kelvin, as I said, that is denoted as the absolute zero because this region is having a negative pressure, which is you cannot compress anything to any pressure less than 0, that is negative pressure cannot arise for a real substance. So no substance can physically be cooled beyond this point, because if it can be done, then we would get a negative pressure which is unphysical, which is not permitted. So that's why it's called as the absolute zero. Now you understand that this number came from such an experiment, and that tells very succinctly that this is the absolute zero below which no substance can be cooled. So just another thing that comes from here is that the pressure comes as proportional to temperature because of this plot where we see a straight line. So pressure is proportional to temperature. So that tells us that P by T is equal to constant, which we get in as one of the gas laws that you will see in when you study gas laws in subsequent chapters. Now, while studying thermal properties of solids, we cannot ignore talking about thermal expansions of of all these thermal expansion of matter, thermal properties of matter, we cannot talk, rather escape talking about thermal expansion of solids, liquids and gases. So, let us talk about the thermal expansion of solids. This is something that is not new to you. You must have seen this when we talked about the Young's modulus and the thermal stresses being developed due to application of temperature, but nevertheless we will do it again very quickly. So, this thermal expansion of solids happen when heat is applied or there is heat given to a system, then the dimensions of the system changes, of a solid material changes, and the dimensions changing means the length can change if it is a one dimensional material, or if it is a two dimensional material the area can change, or if it is a three dimensional bulk material then the volume will change with temperature. So, suppose we have this figure once again, which is this is your initial length L0 and this is the change in length delta L. So, delta L, that is the extension or the expansion of the material, can be written in terms of its original length as L0 and alpha delta t, where alpha is called as the linear coefficient of expansion, and just for making it more clear we will use a L here, just that it is a length expansion. So, delta L equal to L0, alpha L and delta t. Now, talk about area expansion. So, this area expansion can be seen as like this. So, this is my original area A0 and this has area A0 plus delta A, where delta A is the increase in area, and similarly delta A can be written as A0 alpha A and delta T. So, I am skipping all the details, understanding that you know about this, that delta L is proportional to L0, delta L is also proportional to the change in temperature delta T, and alpha L is simply used as a proportionality constant, and so is alpha A here, which is used as a proportionality constant. And if we talk about a volume, then so this is my V0 and this is my V0 plus delta V. I hope you can see that. So, this is a volume. So, this the original volume is this, and this has a volume V0 plus delta V, and so delta V equal to the initial volume and the alpha V and a delta T. Now, it is also easy for small temperature changes to establish a relationship between alpha L, alpha A and alpha V. So, how we do that is the following. Let us take this delta A to be A0 alpha A and delta T. So, I can write down the final area A to be A0 plus delta A, which is equal to A0 plus A0 alpha A delta T, and this is equal to A0 1 plus alpha A delta T. Now, in this particular case, when you have So this can be, so these area that we are talking about has got two dimensions, length and breadth, say for example. And similarly, so this in order to have a relationship between alpha L and alpha A, we look at this result as well. So which is equal to L equal to L0 1 plus alpha L and delta T. And now apparently I should get this area by taking or by squaring it up, so that if I have a square area which is undergoing an expansion, that will simply be L into L. So the new area will be L into L. So if I square it up, I'll have this A, which is equal to L square, which is equal to a L0 square and a 1 plus alpha L delta T whole square. Now I can expand it, this inside term, which is like an alpha 2 alpha L delta T plus alpha L square delta T square. And if I commit myself to small change in temperature, so if delta T is not very large, then delta T square will be even more or even smaller, and in which case I can neglect the last term and I'll have L0 square and 1 plus 2 alpha L delta T, writing this L0 square as nothing but A0. So I'll have a 1 plus 2 alpha L delta T. So now writing A anyway as L square, so I have this relation A equal to A0 into 1 plus 2 alpha L delta T. Now if you compare it with this equation, then you'd definitely get that alpha A equal to twice of alpha L. And similarly, taking a cube of this in order to get a relationship between alpha V and alpha L, one would get it as alpha V equal to 3 alpha L. So the linear coefficient of or the coefficient of linear expansion is related to the coefficient of areal expansion by this relation, and the coefficient of volume expansion is related to the coefficient of linear expansion by this relation. So let us now have a look at typical values, which we always do. Take a look at the typical values of these coefficients of expansion. Typical values for alpha L. I am only quoting the linear coefficient of expansion, but you know that that can be used in order to get the areal coefficient as well as the volume coefficient of expansion. So these are the list of materials. Now we are talking about solids. So this is the alpha L. This is in 10 to the power minus 5 Kelvin inverse. Just to get the dimension correct, let us write down a formula that we have written down earlier. So it's a delta L, which is equal to L0 alpha delta T. This is the relation that we have written down for the change in length. Now this quantity delta L on the left hand side has that same dimension of L0 on the right hand side, so they would cancel each other, and as a result alpha will have the dimension of inverse of change in temperature, which is same as inverse of temperature. So we are using the Kelvin scale of temperature, so this is equal to Kelvin inverse, and the value is quoted in units of in a scale of 10 to the power minus 5. So it's the unit becomes 10 to the power minus 5 and then in Kelvin inverse. So aluminium This is equal to 2.5. Brass equal to 1.8. Iron equal to 1.2. Copper equal to 1.7. Gold, which is 1.4, and glass, which is the Pyrex variety, this has 0.32. So these are some of the typical numbers for the linear expansion of solids, and one can understand that a glass has a much smaller coefficient of linear expansion than that of aluminium. All right. So let us look at also some of the data for the volume coefficient of expansion. We will not provide data for this. They are available in any textbook or any data book that you come across. Let us only give a behavior of alpha v, which is a volume coefficient of expansion. So alpha v for copper and alpha v for copper looks like this and something similar to that. This is the temperature. Now we are expressing in Kelvin, and this is alpha v, again 10 to the power minus 5 Kelvin inverse, and we see that it's only, so this is about 250 Kelvin, which is still below 0 degrees centigrade. It is linear and then it becomes non-linear. So we are mostly talking about the linear regime where the temperature changes are small. So this is something like 500 Kelvin and so on. Now one interesting question is that when you have a hole in a solid, so what happens to holes? So there is a hole of arbitrary shape in, say, a sheet of iron or a sheet of aluminum or brass. So as you change the temperature of this sheet, what happens to this hole? Does it expand or does it contract or does it remain the same? And the question is pertinent and important because of the fact that the entire, so this is that material, solid material. It could be two-dimensional, it could be three-dimensional, doesn't matter. So this material expands, and so what happens to the holes? Does it actually shrink? And in order to answer that, let us look at this figure, which is so these are let us look at so these are the tiles, and so it's a 3 by 3 pattern made of tiles. However, the middle one is missing. Okay? So there is a hole, just as this one. We have taken pattern in order to understand it better. There is a hole there, or there is a gap there, there is no tile there, otherwise this area is tiled with all these are tiles of certain material. Okay. Now what happens is that when one heats it up, it takes, I'll try to draw it to scale so that you understand better. So these are, this is the expanded view of the tiles, and each tile has expanded. So each tile as if had expanded, and the holes have also, the hole has also, the hole which is at the middle has also expanded. Now take a ninth tile which is missing, which is made of the same material, and heat it to exactly the same temperature difference, so that it has the same temperature difference as this case. So I take a ninth tile and induce the same delta T by heating. Now this ninth tile, which was say like this when it was not heated, now so this is the original size, the inside is the original size of the ninth tile, and once when it's heated it takes this form or this shape, expanded shape. Now this ninth tile, which is of the same material and apply the same amount of heat, will now exactly feed this void space. So that tells us that no matter what the shape of the hole is, the hole also expands when it's subjected to a heat. So so that's pretty much about the thermal expansion of solids. There are of course many other things which are important, but we will not go into that too much of details more than this. Let us talk about a very important thing which is called as the anomalous behavior of water near 4 degrees centigrade, which is an expansion property of water, which is a liquid, and what is so special about 4 degrees centigrade is what we are going to see. Now, why this is important is because it has tremendous importance on marine life, on the fishes and other marine animals which are there in say lake or some static water body. Is very important for them. While most materials they expand when heated, but a few do not. For example, the water at 0 degree centigrade, when it's heated, its volume actually decreases till the temperature reaches 4 degree centigrade, and from 4 degree centigrade onwards water starts behaving normally because the volume increases with change in temperature. Okay. However, between 0 degree centigrade to 4 degree centigrade, to remind you, 0 degree centigrade is called the ice point where water starts freezing or ice starts melting, is when you have that the water actually, the volume of water decreases in this temperature range, which is 0 to 4 degree centigrade. Okay. Now, this means that for a given mass of water, it has a minimum volume or a maximum density